Hello everyone. So in this video I'm going to go over diode circuits briefly and basically explain how we can analyze diode circuits, different approaches to analyzing diode circuits using the same routine that we always use that I call the universal approach. Now, if you recall the voltage current characteristic of a diode, we showed it to be exponential in nature, and basically if you plot it, this is what you're going to see. Now, assuming that VD is defined as the potential of this end of the diode subtracted from the other end, and by the way, this end, the positive, and the end that is defined as positive in this representation is called anode, and this is called the cathode. Now, the voltage of the anode minus the voltage of the cathode is what we call VD in this plot. Now, for the positive, until VD reaches a value close to 0.6, 0.7 volts for silicon diodes, the current is pretty small, and then all of a sudden it starts increasing pretty rapidly, hence the exponential nature. And for the negative voltages, as long as you are not close to what we call the breakdown voltage, the current that is passing through the diode is very small. Now, the equation that could define this behavior based on the physics of the device looks like this, and we discussed it. So it's ID equal to IS, the saturation current, times exponential function E to the power of VD, the voltage of the diode, divided by the thermal voltage, which is for room temperature is 0.026 volts or 26 millivolts minus 1. And then we also discussed that for the most part we can ignore that minus 1 and rewrite that equation approximately as IS times e to the power of VD divided by 0.026. So this really is the way, the equation that you can use, in the algorithm that we have described before when it comes to writing the equation for the diode. And if you do that and solve the set of equations that is resulted, that's basically the most accurate way of analyzing the circuit. So let's try that for this circuit, and I'll then move on to explain to you what other options we have if this is not really what we want to do, for the reason that we're going to see soon. So like always, we're going to approach the circuit and circuit analysis the same way. We start by identifying the nodes. So this is our node that is now, by definition of the problem, is assumed to be our 0 volt or reference. Then there's this this node right here, and there's this node up here, which obviously has the value of 5 volts here, so it's a known value. And then the node on the right. So now these two are known values, and then I'm going to call this one V1 and call this one V2. Now obviously in this circuit, if we go by this convention that we defined there, VD, the voltage of the diode, should be defined as V2 minus V1. You just keep that in mind, because if you want to refer to this equation, we just have to keep that in mind. Now, once we're done with labeling the nodes, then we're going to move on to labeling the currents that are passing through each component. And so you look at components, and for each component you define a current. So this would be one current, another current, another current. This is the current that is passing through the diode. So I'm going to do I1, I2, I3, I4, and I'm going to call this ID. And with that, we are done labeling the circuit. So I'm going to move on to now writing the equations. So we start by KCL. So we don't have to do KCL for the known nodes. In this case, the 5 volt and the ground, we don't gain much by writing KCL. But if we want to, then we have to actually define currents for these two branches, but that's not something that we want to do, so we're going to leave them alone. We're going to move on to the nodes, the unknown nodes. just have to be careful. You may be tempted to just ignore the fact that there are currents here and just say I1 plus I2 is equal to 0, at which point that equation is incorrect. So if it makes it easier for you to understand what is going on here, is that basically between these two nodes there is a voltage source connected with the value of 5 volts, and from that voltage source there is a current coming in and there's a current going back to that voltage source. So if you want to redraw the circuit like that, maybe that makes the analysis more understandable for you, then do that. But otherwise just leave it like this and you don't have to write KCL for those two nodes. So for the node V1, you want to start. It's I1 plus ID, that's equal to I2, and for the node V2, it's I3 current going in is equal to I4 plus ID. Then we move on to equations for components. Now we have 5 components here, and therefore we're going to write 5 equations. I1 is going to be equal to 5 minus V1 divided by 3K. So this current is going to be in milliamp. So any other equation that I write, I have to write them in milliamp if I leave this as 3. I can turn this into 3000 and then leave everything as amp, but I'm going to go with 3, which is easy. So then I2 is equal to V1 minus 0 divided by 2. I3 is equal to 5 minus V2 divided by 2. Then finally I4 for the fourth resistor is equal to V2 minus 0 divided by 2. And the fifth equation is the equation for the diode. Now, this is the equation for the diode. So we're going to go like this. ID is equal to, because we happen to actually call the current passing through the diode in our circuit also ID, so that stands basically compatible with the original equation that we had. And then IS E to, now VD is basically like what we said, V2 minus V1. So that would be V2 minus V1 divided by 0.026. At this point, we're done writing all the equations, and we have, as you can see, 7 equations. And let's count the number of unknowns that we have. So we have 1, 2, 3, 4, 5 currents and 2 potentials. So that's 7. So 7 unknowns and 7 equations, and therefore I should be able to find unique values for all the currents in the circuit and the potentials of the nodes, given I can manage to solve these set of equations. So one way to do that is to basically take all the equations for the currents that we have here and put them back into the KCL, at which point I'm going to only have 2 equations and 2 unknowns, V1 and V2. But then if you notice, this is not going to be a simple linear set of equations that needs to be solved. There's an exponential equation there. It's not that big of a deal. You can easily use calculators and that gives you the values. But if you don't have access to calculators or computers, this might be a bit difficult to solve. And therefore, also just doing this mathematical dance here might not give you much of an insight into what exactly going on in the circuit. So the other approaches are based on what we call piecewise linearization of a nonlinear equation. So the same nonlinear plot and nonlinear equation, if I kind of know in which part of this plot I happen to operate in this circuit, then I can linearize this plot around that point and simplify my calculations. And that's what I'm about to explain to you next. So there are three different ways of simplifying or linearizing this function. The most simple, that is called the ideal linearization or ideal definition of a diode, is kind of an extreme. So what you're going to do is to say and I'm going to draw with a different color what that's going to look like. So basically I'm going to use yellow. So you're going to say for all the negative voltages, values for VD, the current is 0, and then for any positive, the current immediately becomes infinity. In other words, you turn this nonlinear equation to two pieces of linear equation right around 0. These switch from one to the other, and it's basically kind of a switch actually. So it says for any negative voltage, the switch is closed, and for any epsilon positive voltage, the switch, it becomes a short circuit. And if you want to write the equations for these two lines, it goes like this. So the alternative one for writing equations, and let me actually go back and use a different color because I want to be consistent in terms of what color I use for what equation. So let's say I'm going to do green for this extreme case, and then I'm going to use green also to write the equation. There you go. So the equation goes like this. The green approximation is this: ID is equal to 0 if VD is negative. That's the equation for this line, ID equal to 0. And then as soon as it switches to the other one, the equation is actually this: VD is equal to 0 for any positive current. So this equation is for this line, VD equal to 0, and ID equal to 0 is the equation for this line. So with this very simplistic approximation, I'm basically simplifying the math to an extent that just by looking at it I can tell what I should expect, assuming that this approximation is accurate enough. So let's see what is going to change here. So if that's the case, then as it's clear, I have to actually choose which one of these two are true, because I can just put one equation for that component, and based on where I happen to be, one of these is correct. So this equation right here is going to go away. So I'm going to remove this equation, the last one, which was based on the accurate approximation or accurate definition of the physics of the diode. And instead, now I have to make a choice and say either ID equal to 0 is the equation that I'm going to use for the diode, or VD equal to 0 is the equation that I'm going to use. Let's say I have no clue. So I just pick one. I'm going to say, in this case, choose ID equal to 0. So if ID is equal to 0, I'm going to put it there, and let's see what happens. Now, when I write ID equal to 0 here, what I'm basically saying is that VD is negative, because that's the only condition under which ID is going to be 0. So the test for whether or not this assumption was correct is to actually solve this new set of equations and then go back and calculate VD and see if VD actually is a negative number than what the assumption that I made was going to be correct. So let's quickly move on and do the math at this point. So ID equal to 0 simplifies everything. First of all, it means that I1 is equal to I2, and then it also means that I3 is equal to I4. Now if you put these here, use these and these for equation, basically what it means, you do the math and you're going to see it. These are basically turning to voltage divider equations. So V1 becomes 2 over 5 times 5, which is 2 volts. And then from these two and those definitions, you're going to get V2 is equal to 2 over 4 times 5, which is 2.5 volts. Now from all of this, then you know VD, which is V2 minus V1, is equal to 0.5 volts. So now this is the moment of the truth. VD is 0.5. For ID to be 0, VD had to be negative. So therefore this assumption that I made is incorrect. Now what I have to do is to now correct that assumption. Well, the only other option is left is this one that has to be correct. Now we're going to make that assumption and redo the circuit. So I'm going to go back and remove all the math that I did based on the wrong assumption. Now if you're doing this for homework, you don't have to remove anything, you just do it again with the correct assumption. So this time the equation that I'm going to use is going to be VD equal to 0. So VD equal to 0. Now again, for this to withstand, ID has to be a negative number. So once I solve this set of equation, the test for the truth of the assumption is if ID turns out to be a positive number. So let's see if that's the case. So VD being equal to 0 means V2 minus V1 in this case is equal to 0. In other words, V2 and V1 are equal to each other. And so V2 is equal to V1, and you can actually you can do the math and see that once you do the math, the voltage turns out to be 1 divided by 2.2 times 5, which is 2.27, 27, so it's like that, roughly about 1.27. And if you use that, then you can calculate I3 and I4, for example. So from this, ID becomes I3, which is 5 minus 2.27 divided by 2, and minus I3. This was sorry. So the ID would be I3 minus I4. Sorry. So I3 would be 5 minus 2.27 divided by 2 minus 2.27 divided by 2 again. So 5 minus 2.27 is 2.73. So you can see 2.73 minus 2.27 is a positive number divided by 2. So ID actually from this equation turns out to be a positive number, and therefore our assumption obviously holds. Now I didn't have to do any of this because we already tested the other option and that was wrong, so therefore the only option that is left has to be correct. Anyway, now this is a simplified, very simplified approach to an extent that the approximation that you're going to get is actually not close enough to the actual values that you would get if you have used the other equation, the actual equation. And I encourage you to use values here and see that that's actually the case. Just use some reasonable value with IS, say 10 to the minus 12, and solve this set of equations based on what we just saw. And keep in mind, if you're using 2 and 3 here, then IS has to be also in milliamp, not amp. So if 10 to the minus 12 is amp, then you have to basically multiply it by 1000. So 10 to the minus 9 would be the value that you use in the equation if you wanted to solve that set of equation. And based on that, therefore, you're going to get a value. Then compare that to this value that we just calculated it here, and I'm sure you're not going to get values that are very close to each other. I at least not close enough. So then the next step that you can take in order to do a better approximation is what we call again a step forward for linearization in terms of accuracy. And in this one, I'm going to use a different color now. I have to somehow blue. So the blue one assumes that for any negative value of the voltage, the current is 0, but then extends all the way to what we call the built-in voltage of the diode, and then assumes that the diode turns on and turns into a short circuit basically at that point. So you can see, well, we're not really ignoring this offset in this new approximation. So let's actually write the equations this time. I'm going to use blue. Not light blue here, I'm just going to use blue. So this new approximation goes something like this for the blue approximation. So ID is equal to 0 this time, as long as VD is equal to the built-in voltage of the diode. This for the silicon diode is something close to 0.6 or 0.7. It's going to be given to you, and then after that, then VD just stays constant as V gamma for any positive current. So this is the new set of equations that we can use, which is a better approximation. So let's now use this one. So we go back, we have a new model or equation for the diode. Based on this new equation, again we have a choice to make. We have to either assume that the diode is off or the diode is on. Now the diode would be only on if the voltage V2 minus V1 is equal to V gamma, and at which point you're going to get a current, positive current passing through. So then again, let's make the wrong assumption. Let's assume that that's the case and V gamma is equal to 0.6, and go with the second option that we have here. So let's say the equation that we choose is that VD is equal to 0.6. Now if that's the equation that I'm going to use for the diode, I am explicitly or implicitly assuming that the current that is passing through is positive. So when I solve this set of equations, I'm expecting ID to become a positive number. Now if that's not the case, then the assumption that I made is incorrect, right? So then again, based on this, I'm going to do V2 minus V1 is equal to 0.6, right? And I move on to solve these set of equations and try to calculate the currents, all the currents. Now I assure you, when you do that, you quickly realize that actually from this set of equations, ID turns out to be, as a result of this, ID turns out to be a negative number. And when you make that, when you see that, then you look at this definition and you clearly know that the assumption that you made is incorrect. Now to prove that for you, I can make the correct assumption, because with the correct assumption the math is going to be pretty simple, and show you that that's going to be consistent. In other words, if I assume ID is equal to 0, then VD is going to be less than 0.6 volts. So let's do that. ID equal to 0. So as soon as I make that assumption, again it goes back to I1 being equal to I2 and I3 being equal to I4. So the same thing that we saw before is going to happen. In other words, V1 becomes 2 volts and V2 becomes 2.5 volts, basically voltage dividers right in the middle and 5. and therefore VD is 2.5 minus 2, which is 0.5 volts, and 0.5 volts is smaller than 0.6. Therefore, this assumption that I made is correct. Okay, so now this basically is what this model is what a lot of times is used for diodes to do like back on the envelope kind of a calculation. How do you know which one to pick? In the problems, it's going to be given. If you're just given a problem to solve, if it says ideal diode, you use this green approximation. If it gives you the value for V gamma or the built-in voltage of the diode, it's basically telling you to just use this approximation. How do you know later on? Well, if you're just on your own, if the voltages that exist in the circuit are comparable to V gamma of a diode, then you better consider V gamma and use the second approximation. If the voltages are large, if like this voltage right here was really large, or you're dealing with hundreds of volts, sometimes just ignoring V gamma is not going to make big of a difference, and you're fine if you make the oversimplified and ideal approximation for the diode. Now, finally, I'm going to talk about the last kind of approximation, which is the most accurate, and this time don't have a good option as for the color. I'm just going to stick to this one. This time we're going to assume that the pink, the current is 0 for all the negative values. It reaches here and then it turns into a different line with a certain angle. So we are basically not saying that the diode, when it turns on, it actually turns into a just straight line or a short circuit or a constant voltage for that matter. The voltage actually changes as the current changes. So it's as if the equation changes to something like this. So the current ID is equal to 0 for any voltages that is less than this voltage right here. So V less than, what I'm going to call it V knee at this point, just a made up name. It's close to the breakdown voltage, but it's not exactly equal to the breakdown voltage, but you can a lot of times use the breakdown voltage for that voltage. And beyond that, the second line goes like this. Then VD is equal to V knee plus RD, the resistance associated with the diode, times the current of the diode ID. Now, where's that RD coming from? Well, RD is the slope of this line. And that slope actually is not a constant slope. It depends really where you think you're operating, and based on that, it's really the derivative, right? Derivative of this equation right here, 1 over the derivative of this equation, that gives you RD. Okay, it's the slope, right? So you have to basically, the slope is the same as the derivative of this function. So the derivative of this equation is basically IS divided by 0.026 e to the VD divided by 0.026. And 1 over that is RD for a specific value of VD that should be either estimated or given by the equation, by the problem. So now what it really means is that you're taking the diode, this equation right here, if that's the equation that you're using, and you're replacing it with a model like this. A power supply, which is equal to a battery or supply, with that V knee, and then RD. So this is, you're equating the diode with something like this. And by the way, when you were using this model, you were equating the diode with the first one, the green one. You're equating diode here with a short circuit and here with an open circuit. With the blue, you're going with an open circuit and a constant power supply, just V gamma. So if you really want to maybe go back here and make those changes in the circuit to help you understand which one of, like, how any of these approximations impacts the circuit better. Again, for ID equal to 0, you completely replace the diode with an open circuit. You're basically removing it. For VD equal to 0, you're turning it into a short circuit. For VD equal to V gamma, you're replacing it with a power supply like this, or battery like this, with the voltage equal to V gamma, or 0.6 volts. And then finally with this one, you're turning it into a power supply and a resistor in series. So you can put that back in here and write these equations, but you don't have to. We already know what the equation is. You can just put it in there as opposed to replacing it over there. So it's an option that you have in order to visualize how you're modeling the diode. Okay, I'm going to stop here. We're going to hopefully do more examples to learn which model, which approximation to use, and how to use them in future videos. Thank you for your attention.